The topic of today's video will be orthogonality and recurrence relations for Legendre polynomials, right? So I will start with the orthogonal behavior of Legendre's polynomials. As you know, what is orthogonality in vectors? Two vectors are said to be orthogonal when their dot product is 0, right? So in case of polynomials, we say that two polynomials are orthogonal to each other when they are multiplied and integrated over a suitable range, and they give the resultant at 0, right? So I will write that property of orthogonality in case of Legendre's polynomials. So that is integral -1 to 1. This is the range of integration for the orthogonal polynomials, right? And if I write Pmx and the other polynomial as Pnx, then this is 0 if m is not equal to n, and is equal to 2 by 2n plus 1 if m is equal to n, right? So when these two indices are different, the resultant is 0, otherwise it is 2 upon 2 to the power 2n plus 1, right? And why they are integrated over this range -1 to 1, the reason is that if you remember the graph of those few orthogonal polynomials, they were bounded at x equal to 1 and x equal to -1, so the range is taken from there, -1 to 1, right? So the proof of this goes like this. Proof, I will take two cases. First case, if m is not equal to n, if m is not equal to n, right? This is case 1. Suppose Pmx and Pnx are solutions of Legendre's differential equations, right? That is 1 minus x square u double dash minus 2x u dash plus m plus 1 u equal to 0, right? So for this differential equation, the solution is Pmx. So that's why I have written here m plus 1, right? And for this 1 minus x square, I am changing the variable for it, v double dash minus 2 x v dash plus n plus 1 v equal to 0, right? So you can see that the first is involving m, while the second one is involving n, right? So Pmx is a solution of this thing, and Pnx is a solution of this second differential equation, right? So now what will we do? We'll just multiply the first equation by v and the second by u, and we'll subtract that, right? So you multiply first by v and second by u and subtract, right? Then 1 minus, this will give 1 minus x square u double dash v minus v double dash u. This is for the first term, right? First term. And for second terms, 2x will be taken common, I think. Minus 2x will be taken common, and inside bracket will be having u dash v minus v dash u, right? And for the third term, uv will be taken common, and inside bracket you will be having m square plus m minus n square plus n. That will give you m square minus n square plus m minus n, and m minus n multiplied by m plus n, and ultimately m minus n will be taken common, and inside bracket you will be having m plus n plus 1, right? So on simplification you will obtain this, right? Okay, now focus on these two terms, right? They can be written as d by dx of 1 minus x square, this term, and since the differentiation of this term is minus 2x, and differentiation of this thing is this thing, right? So I can write it as u dash v minus v dash u, right? You should check it by yourself. You should apply the product rule. You would take this as the first term, this is the second term, right? And when you apply the product rule, you will, on applying product rule for this, you will get these two terms, right? You can check this. The first term as it is, and differentiation of second term, that will be u double dash v plus u dash v dash minus v double dash u minus v dash u dash. So ultimately u dash v dash will be cancelled out, and the first term will be this thing, right? And then second rule, because it is chain rule, then second term will be plus this thing, right? You can see that, and differentiation of this thing, that is minus 2x, right? So these two terms can be written as in this form, derivative form. And if I take this on the right hand side, then it will become n minus m and m plus n plus 1 uv, right? Now integrating both sides, integrate both sides with respect to x. And since it is already d by dx, the integration will be cancelled, and integration within the range minus 1 to 1. I should write that, integrate within range minus 1 to 1 with respect to x, obviously. And it will give you 1 minus x square and u dash v minus uv dash, and the range is minus 1 to 1, and since this is a constant, n minus m, n plus m plus 1, integration minus 1 to 1 u v dx, right? And if you plug the upper limit in place of x, that will give you 0. Putting the lower limit in place of x, that is again giving you 0. So the left hand side is ultimately equal to 0, and right hand side is n minus m, n plus m plus 1, and minus 1 to 1. The value of u, you can see that we have assumed that Pmx is the solution of this differential equation in variable u. It means that the solution is u, that should be equal to Pmx, right? And for the second differential equation, v should be actually equal to Pnx, right? So I will replace those u and v by Pm and Pn. Pmx, Pnx dx, right? And now you can take this constant in the denominator, because you know that n minus m is not equal to 0. You are assuming the case that m is not equal to n, right? Since m is not equal to n, it means that this is non-zero term, and you can bring this term in the denominator, right? Be careful at this point. You cannot always bring any constant over the 0, right? Under 0, right? Since it is a non-zero, you can bring it under 0, right? So ultimately it will give you minus 1 to 1 Pmx Pnx dx is equal to 0 divided by this whole thing. You know that this is not equal to 0 since n is not equal to m, and this is also not equal to 0. Why? Because n, m and m are positive integers, right, or non-negative integers. They can be 0, 1, 2, 3. If you put both 0, 0, you will get what? If you put 1, 2, you will get some number, right? There is no chance that this constant will be equal to 0, because n and m are non-negative numbers, right? So we can write this equal to 0. This goes in the denominator, and that gives you 0. So this is a small proof for the case when m is not equal to n, you are getting the result as 0, right? Now I will try to prove the second one, this one. If m equal to n, right? So we will start with this integral, integral minus 1 to 1 p nx into Pnx, right? Because m is equal to n, and I will use that Rodrigues formula. Since we know that Rodrigues formula and generating functions has many applications in proving these facts, orthogonality and recurrence relation. So I will be using that Rodrigues formula here in order to reach this point, 2 by 2n plus 1, right? So putting the value of Rodrigues formula, that was Pnx is equal to 1 over 2 to the power n factorial, and dn upon dxn of x square minus 1 to the power n, right? So I will use that 1 over 2n n factorial, that will become whole square because we have 2pn here, right? And minus 1 to 1, and value was dn over dxn, and value of Pnx, that was 1 minus x square to the power n, and since it is a square, so that will be whole square of this thing, right? Okay. And now what I will do, I will just first try to take negative common out of this. If I take negative common, that it will become minus 1 to the power n will be common, and since here we have 2, so ultimately it will be minus 1 to the power 2n. So that will give you 1 upon 2n factorial whole square, and taking minus 1 to the power 2n common, we will be left with d. I can write it as d. D by dx can be written as d dn x square minus 1 to the power n whole square, right, dx, right. And since it is an even power, so minus 1 to the power even power will be plus 1 ultimately, so I will replace it by plus 1 n factorial whole square, and this will become minus 1 to the power n dn x square minus 1 to the power n dot dn x square minus 1 to the power n dx, right. Okay, now I will assume this integral as capital I, say, and let it be equation number 1, right. Now we will evaluate this capital I, and then after finding its value, we will plug that value here in equation number 1. So now capital I equal to integral minus 1 to 1 dn x square minus 1 to the power n dn x square minus 1 to the power n dx, right. You can see that here we have two functions u and v, and I have to apply that rule of by parts, integration by parts here. This is my first function, second function, right. So integrating by parts, first function is written as it is, and integration of second function, right. So if you integrate this, you will get dn minus 1 x square minus 1 to the power n, right, because we are already having nth derivative, and when you integrate it once, you will get n minus 1th derivative, right. One derivative will be cancelled, because integration and differentiation are inverse operators. They cancel each other, like at this point we had derivative, and when we integrated, that d by dx was cancelled with the integration symbol, right. Same thing is happening here. Okay, and then minus integration, I should put limits here, minus 1 to 1, and differentiation of the first function, that will give you dn plus 1 x square minus 1 to the power n, and integration of the second function, that will give you dn minus 1 x square minus 1 to the power n dx, right. So this is what we got after applying the rule of by parts 1 times, right. So on putting the limits, if I put the limits, can we put limits at this point? The first thing is that you can see that you focus on this thing. This is quadratic, and you have n power here, so ultimately it will be a polynomial of degree 2n, right, because you have 2 here and n here, so it will be a polynomial of degree 2n, right. First thing is that, and you are differentiating it with how many times? N times, right. Or you just leave it, you focus on this thing, rather you focus on this thing. This is a polynomial of degree 2n, right, and this is of degree n minus 1, degree which is of course less than 2n, n minus 1 is less than 2n, right. So you hope that every time you will be having x square minus 1 here, because you are differentiating a 2n degree polynomial how many times? N minus 1 times, so there will be always a factor of x square minus 1 in the value of this thing, right. So due to the presence of x square minus 1 in the value of this thing, I am not evaluating this. However, on evaluation, you will always have x square minus 1 in its value, right. So on plugging the 1 and minus 1 will give you 0 in both cases, right. So I will write that will give you 0, and why it is giving 0, you should know that. The reason is this, right, and minus 1 to 1, and yeah, dn plus 1 x square minus 1 d n minus 1 x square minus 1 and dx. So this is the result, or 0 can be removed like this, right. So this is the result after getting after integrating once, right? So on integrating it once, I am getting dn plus 1 and dn minus 1. So on integrating it twice, I will get, here I will get minus 1 whole square, right? Dn plus 2, dn minus 2. So on integrating it n times, I have to generalize that result for n. I will write the result directly, right? So integrating it once is producing negative minus 1 to the power 1. So on integrating it n times, will produce minus 1 to the power n here, and dn plus n, dn minus n, so on, right? So generalizing it, right, on integrating it n times, or should I write on applying that rule of by part n times, right? We'll get I equal to minus 1 to the power n minus 1 to 1 and d n plus n, right? 1 will be replaced by n, x square minus 1 d n minus n x square minus 1 dx, right? Now this will become d2n x square minus 1, and this will become d to the power 0, means do not differentiate, you will just write x square minus 1, right? So that will give you minus 1 to the power n minus 1 to 1 d 2n, this for here we had n, right? X square minus 1 n, and this will become x square minus 1 to the power n dx, right? And it will be, you can see that this is a polynomial of degree 2n, right? And differentiating it 2n times will produce a constant, right? So the constant will be 2n factorial, obviously, because the highest term in this polynomial will be x to the power 2n. It is clearly visible from here, and differentiating it 2n times will give it 2n factorial, right? So we'll write that 2n factorial, and this is x square minus 1 to the power n dx, right? So I can take this constant outside here, and minus 1 to the power n, I should write n plus 2n, yeah, why 2n? Because I can write it as 1 minus x square to the power n dx. Taking minus 1 to the power common from here will produce a 2n power here that will be added up with this thing, right? So that it will become, again will become plus positive, right? And 2n factorial, it will become plus 1, and since it is an even function, you can see that even function, since if you replace this x by minus x, you will again get the same function. So I'm applying that property of an even function, 0 to 1, the limits will be changed, and 1 minus x square dx, right? So now it remains to solve this definite integral. You focus on this definite integral. I should put x equal to sine theta, right? And then dx is equal to cos theta d theta, right? So then it will become I equal to integral 2 times 2n factorial. If you put 0, you will get theta equal to 0, and on putting 1, the upper limit of theta will be pi by 2, and 1 minus sine square will be cos square theta, cos to the power 2n theta, and cos to the power 2n plus 1 theta d theta. So ultimately you will reach here. Now it remains to solve this definite integral, and we have a special formula for this. If I remember it correctly, that was Wally's formula. I will write that, and that is a shortcut to evaluate this type of integral with the limit 0 to pi by 2, and that goes like this. This is odd power, right? 2n plus 1, then here we have 2n minus 1, then 2n minus 3, and here we should have 3, right? And 1 less than this, that will be 2n, right? 1 less than this, 2n minus 2, and 2n minus 4, so that should be 2, right? Okay, so this is the result of this integral. This is called Wally's formula, right? Okay, now I will yeah, that is evaluated. Capital I is known, and I will plug this value here in equation number 1 to get the value of this thing, right? Put in equation number 1 again, right? So that was integral -1 to 1 p nx dx is equal to 1 over 2 to the power n factorial whole square, and the value of I is this much. Okay, 2 times 2n factorial, and you can see that this whole series 2n minus 2 up to 4 2, and the denominator is 2n plus 1, 2n minus 1 up to 5 3 and so on. Okay, right. Now you can take you can see that in each factor 2 can be taken as common, right? These are even factors. So how many 2's will be there on taking common? 2 to the power n will be common, right? So you will get 1 by 2 to the power n factorial whole square, and 2n factorial. So if you take common here, you will get how much? 2 to the power n will be taken common, and inside the bracket you will be having terms like this. N, from here you will get n minus 1, so on, and from here to 1. So ultimately that will become n factorial, right? And in the denominator we are having 2n plus 1, 2n minus 1 up to 5 3 1, right? Okay, so I think 1 2n 2 to the power n can be cancelled out. Okay, and this will become n factorial. So 1 n factorial can be cancelled out with this thing. So ultimately you will be left with the 2, this 2, right? This 2n factorial, and in the denominator you will be having 1n factorial, I think. Yeah, and here you will be having how much? 1 over 2n plus 1. Should I write this 2n plus 1 here? 2n plus 1, and starting with 2n minus 1, 2n minus 3 up to 5 3 1. Now if I apply here, yeah, all of those odd factors will be cancelled out, and 2 and 2 to the power n will be again common. Okay, and n factorial will be common. 2 to the power n, I think this was 2 to the power 2n, sorry, 2 to the power 2n, yeah, 2 to the power 2n. Now it is correct. 1 2 to the power n will be there, 2 to the power n, right? Now we can expand this, that will give you 2 by 2n plus 1. Okay, if you open this 2n minus 1, 2n minus 2 up to 5 4 3 2 1 divided by, this is n factorial, this is 2 to the power n, and here we have these all of those odd factors, and you can see that these odd factors starting from here, these will be cancelled out, 2n minus 1 2n minus 1, and 2n minus 3 2n minus 3 up to so on. All odd factors will be cancelled out. So in the numerator will be left with even factors, 2n minus 2 2n minus 4 up to 4 2, right? And then I can take common, right? I should cancel those terms, 2n minus 1 2n minus 1, and 5 with this 5, this will be obviously cancelled, this 3 will be cancelled, right? Okay, so you will be left with these even factors, and how many are these? 2 to the power n, you can take 2 to the power n common, n factors are there, so 2 to the power n will be taken common, and that should be 2 to the power n and n factorial, right? N factorial 2 to the power n, right? Okay, and on cancellation it will give you 2 by 2n plus 1, right? So this is a proof of that orthogonality condition in case when m is equal to n, right? So now I will try to prove another thing, that is the recurrence relations for these Legendre polynomials, right? Now recurrence relations. As you know that what is a recurrence relation? A recurrence relation is a relationship between the terms of a discrete numeric function, right? Suppose you have Pn as a discrete numeric function, you call it Legendre polynomial. And the relationship between the Pn or Pn minus 1 or Pn minus 2 and so on, the relationship between the terms of a discrete numeric function is called a recurrence relation. That's the definition you have already learned in this unit, right? But since we are dealing with the Legendre polynomial, and Legendre polynomial is generated by Pn, right? That is a kind of recurrence relation, obviously. And obviously, the domain of a discrete numeric function is natural number, right, or non-negative integer. And in this case, you know that the P, and when you write Pn, the suffix n can be 0, 1, 2, 3, 4, so on, right? It cannot be negative. It cannot be in decimals, right? It is a polynomial. It gives the values P0x, P1x, P2x, P3x, and so on. So it indicates that Pnx can be considered as a recurrence relation. Remember that a recurrence relation has a domain which is non-negative integer, right? 0, 1, 2, 3, and so on. And range is any real number. And in all of these Legendre polynomials, n equal to 0, 1, 2, 3 is allowed. No negative n is allowed, right? No fractional n is allowed. That's why we can try to find the recurrence relation for these Legendre polynomials, right? Okay, so there are 5 or 6 recurrence relations. 1, 2, 3. The first 3 are kind of fundamental relations, right? They can be derived with the help of that generating function formula we discussed in our last video, and the last 3 can be derived after manipulation of the first 3, right? So you should first remember the first 3 of them, and then later 3 will be derived by manipulations, right? Okay, so I will start with the generating function formula you studied in last video, right? So generating function was since summation Pn h to the power n. I am skipping writing x here. You write x here, but I am skipping that x, right? It is understood that this Pn is a function of x, right? And multiplied by h to the power n, that was equal to 1 minus 2xh plus h square to the power minus half. It indicates that a Legendre polynomial is actually the coefficient of h to the power n in the expansion of this, right? So that thing can be written in this way also, right? Okay, so using this generating function is generating function for Pnx, right? Okay, so I will differentiate it with respect to h, right? Differentiate with respect to h, right? So on differentiating it with respect to h, it will give you summation, and I am not writing the range here, right? Okay, Pn n h to the power n minus 1. This is a differentiation with respect to h, and here it will give you minus half 1 minus 2xh plus h square to the power minus 3 by 2, and again the differentiation of this thing will give you 2h minus 2x, right? And this 2 can be cancelled with this thing. Okay, and this will give you summation Pn n h to the power n minus 1, and this 2 will be cancelled, and negative can be taken inside, so we will be left with x minus h, and this thing again you can see that this thing can be broken in this way: 1 minus 2xh plus h square minus half, and 1 minus 2xh plus h square, right? This will be multiplied with the left hand side, and x minus h, and again you see that this term, this numerator part is actually this thing, summation Pn h to the power n, right? Okay, So now what I will do, I will equate the coefficient of h to the power n on both sides. Equate coefficients of h to the power n on both sides, right? So be careful at this point. Since we have, how many terms are there on the left hand side? 3 terms. First is this thing, second is this term, and third is again this, 3 terms. On right hand side we have 2 terms, 1 and 2, right? So in each of these terms there will be summation. First thing is that, and h to the, we have to pick up the coefficient of h to the power n. So be careful. If you multiply this one with this thing, that will be summation pn and h to the power n minus 1, right? But we have to pick the coefficient of h to the power n, right? So h to the power n coefficient will be given by this thing, right? So you have to just scale up this, because if you replace n by n plus 1, you will get h to the power n for the first term, right? Okay. And the coefficient of h to the power n from the first term, that is obtained by multiplying the summation with 1, right? I'm not talking about the all 3 terms, I'm just talking about the first term. So I've removed those arcs. Okay, now see the first term. You have to pick the coefficient of h to the power n. Yeah, you should just scale up this, n should be replaced by n plus 1, and in that case the coefficient will become p n plus 1 to n plus 1, right? And this is the coefficient of h to the power n obtained from the first term, right? Now we'll talk about the second term. See the second term, right? When you multiply this with 2xh, this h will go inside and h to the power will be n, right? And in that case the coefficient will be minus 2 x n p n, right? No need to scale up. Third term. This is the third term. When you multiply this with h square, it will be added up and it will give you h to the power n plus 1, but you need h to the power n, so you have to scale down, and that will give you plus p n minus 1 into n minus 1, right, equal to. Similarly here, first term, that is x pn, the coefficient will be x pn for h to the power n, but if you multiply this with h, that will produce h to the power n plus 1, but you need coefficient of h to the power n, so you have to scale down, n should be replaced by n minus 1, and that will give you negative p n minus 1, right? And on simplification it will give you n plus 1 p n plus 1. I think these 2 terms, first and second, they have the same suffix pn, it should be taken here, right? Minus 2n plus 1 x pn, right? And these 2 have same suffix, right? I think that will be cancelled, plus n minus plus n times pn minus 1 equal to 0. This is the first recurrence relation. I am calling it recurrence relation A, right? And why we are calling it a recurrence relation, you can see that here we have a discrete numeric function, that is pn, and it is related to its previous or next terms. Pn is related to pn minus 1, pn plus 1. That's why it is a recurrence relation, right? Okay, or you call it difference equation also. Now this is the first recurrence relation. I will try to obtain the second recurrence relation, but I will need this equation again. I will call it equation number 1, or should I call it A, small a, right? Okay, and this is, okay, this is A. I should call it A, recurrence relation A. Now I will start recurrence relation B. And in order to derive recurrence relation B, I will again start with this thing, right? Since summation pn h to the power n 1 minus 2xh plus h square to the power minus half, right? Now this time I will differentiate it with respect to x, right? Okay, differentiate with respect to x. So that will give you, remember that pn is a function of x, and I have skipped writing that x in bracket, right? So when you differentiate it with respect to x, this will become pn dash x, right? Okay, so it will give you summation pn dash x. I'm not writing that x, h to the power n, and on differentiating this you will get minus half 1 minus 2xh plus h square to the power minus 3 by 2 and for this you will have minus 2h in the multiplication, right? So this 2 and 2 will be cancelled out, and that will become, and you should write this as 1 minus 2xh plus h square to the power minus half divided by 1 minus 2xh plus h square, as I written in here, right? And then you multiply that thing here, you will get 1 minus 2xh plus h square multiplied with this thing, summation Pn dash h to the power n is equal to, and this will be cancelled, you will be having h and this with the power minus half, and that should be replaced by again this summation Pn h to the power n, right? Okay, so we have reached at this point, and if you see this equation number A, they are almost same, right? Okay, and I will call it equation number B, and I will divide these two, A and B, right? So that this factor will be cancelled out, and we'll obtain a new recurrence relation, right? So divide B by A, so that will give you summation Pn dash h to the power n divided by left side summation Pn n h to the power n minus 1 equal to this upon this, so h upon x minus h, this will be cancelled. Yeah, now on cross multiplying you will get x minus h summation p n dash h to the power n equal to summation, since this is h, this it will go inside bracket, and it will become h to the power n, you can see that, right? Now what I will do, I will compare the coefficient of h to the power n again to obtain a new recurrence relation. I want to get rid of this summation, right? So we have to do comparison and equating coefficients of h to the power n, right? And since you can see that here we have two terms, the first is x multiplied with this thing, right? And the coefficient of h to the power n will be Pn dash and x, right? And if you try to obtain the second term on multiplying these two, you will get h to the power n plus 1 inside summation, right? But you need the coefficient of h to the power n. This time you have to scale down, and that will produce minus of p n minus 1 dash equal to n Pn. So this is I think second recurrence relation B. Okay, so far we have derived two recurrence relations, and both of them can be derived from that generating function. That's why generating function is very important, right? And now third recurrence relation, and for that I have to differentiate that again with respect to x, okay? And I will replace the value of x Pn dash from here, I think, yeah. Right? The idea is that to obtain a new recurrence relation, however, this is just a manipulation, right? One can differentiate any recurrence relation and just replace any term of it, and will have a new recurrence relation. But to get the third recurrence relation, what you should remember that you have to differentiate it with respect to x first, as I did here. Where is that? Yeah, and I will replace the value of this thing x Pn dash from B. Right, so you need to remember all those paths at least, right? So derivation for third recurrence relation, for that what I will do, I will use this thing B, using B, yeah, from B, and what is that? 1 minus 2xh plus h square summation Pn dash h to the power n equal to how much? H times summation Pn h to the power n, right? Okay. Or should I multiply it inside? It will become h to the power n plus 1. And I want to use this, but I cannot use this until I get rid of this summation sign. So in order to get rid of this summation sign, I have to do comparison, and for that I will compare the coefficient of h to the power n first, right? So equate coefficients of h to the power n, and be careful at this point. You have three terms on the left hand side. If you see the first term, the coefficient of h to the power n will be simple, Pn dash, right? And if you try to pick up the coefficient of h to the power n in the second term, you can see that this is h to the power n, it will become h to the power n plus 1. So you have to scale down this time to pick up the correct coefficient, right? So that will give you minus 2x, yeah, and Pn minus 1. This will become n minus 1. Suffix will be scaled down, right? And see the third term, it will produce h to the power n plus 2, and to get h to the power n you have to scale down twice, and that will produce plus p n minus 2 dash, right? And here you have to get h to the power n, so that will produce Pn minus 1. Okay, now I want to use this. I need the value of this thing, x Pn dash, but I don't have x Pn dash here. Should I scale down this by 1? Scale up, sorry. So that will become Pn, right? So replace n by n plus 1. So that will produce p n plus 1 dash minus 2x Pn dash plus Pn minus 1 dash Pn, right? And now I can use the value of this thing. X Pn dash from, is that b, right? Using b, and the value of x Pn dash is equal to p dash n minus 1 plus n Pn, right? So I will use this value here, right? That will give you implies Pn plus 1 dash minus twice p dash n minus 1 plus n Pn, and plus p dash n minus 1 equal to Pn, right? Okay, that will give you Pn plus 1 dash minus, and this will become minus p n minus 1 dash. There are 2n Pn that will go on the right hand side, give 2n plus 1 Pn. So this is the third recurrence relation. Right. Okay. Now the fourth recurrence relation is the easiest recurrence relation that can be obtained by just subtracting these two, c minus b. If you subtract these two, then this term will be cancelled. You can see that. So that is very easy. I will do that here. Recurrence relation D, and that is obtained by c minus b. Subtract c from b, and you can see that if you subtract this minus this, that will give you x p n dash minus p dash n plus 1. This will be cancelled, second term will be cancelled, and here you will have n p n n minus this thing, that will become minus of n. So minus will be taken from minus of n plus 1 Pn, right? Okay, and you can switch these sides. I think if I multiply this with negative sign, that will become p dash n plus 1 minus x Pn dash equal to n plus 1 Pn, right? This is the fourth recurrence relation, D, right? And similarly, I will try to obtain fifth and sixth recurrence relation from these first, second, third, and fourth, right? Now fifth recurrence relation that can be obtained from this recurrence relation. You can see this from D, from recurrence relation D. You should just find the value of p dash n plus 1 equal to x Pn dash plus n plus 1 Pn, right? And if you scale down it by 1, replace n by n minus 1, that will produce p dash n equal to x pn minus 1 dash plus n pn minus 1, right? And now what I will do, I will call it equation number c, what is that, b, and this should be small c, right? And if you see this b and you try to remove this term, I should take the negative sign here, okay, minus, and this will become equal to, okay, that is also possible. And now if I multiply this with x, right, then this term will be cancelled with this thing on subtraction, right? So what I will do, I will see small c minus x multiplied by capital B, right? So this is the operation you have to remember in order to reach this fifth recurrence relation, and on doing so I will get Pn dash and negative of that thing, that will produce negative, and x should be multiplied, minus x square Pn dash, and this will be cancelled, and here n Pn minus 1 minus nx Pn, right? So it will give you 1 minus x square Pn dash, and you will take this term here, plus nx Pn equal to n Pn minus 1. So this is the fifth recurrence relation, E, right? And now the last recurrence relation, and that is obtained from that recurrence relation number A by just splitting this term. This is 2n plus 1, it should be written as n plus 1, right? And then I will use this recurrence relation fifth to obtain a new recurrence relation. That is just manipulation, nothing, right? So last, F, using recurrence relation A, and that is n plus 1 p n plus 1 minus 2n plus 1 times x pn plus n pn minus 1 equal to 0, right? So you should just split this term, and that is n plus 1 pn plus 1 minus n plus 1 x pn minus nx pn. You can see that I have broken this term in two terms, right? Plus n pn minus 1 equal to 0, right? And the reason for doing so is that I should use this, you can see that these two ends, this minus this, yeah, it can be replaced. The right hand side, if you take in on the right hand side this term, then these two terms will be same, and the value will be this, right? So using E, right, and that will give you n plus 1 p n plus 1 minus n plus 1 x pn and minus nx pn. You should just replace the value of this thing. If you focus this term, this is equal to 1 minus x square pn dash plus nx pn equal to 0, so that these two terms will be cancelled out, right? Yeah, okay, and you will get n plus 1 pn plus 1 minus, this will become n plus 1 x pn plus 1 minus x square pn dash equal to 0, right? Or you can write it at this way also, 1 minus x square pn dash plus n plus 1 x pn, this term and this term, right? N plus 1 is not x, p n plus equal to n plus 1 x pn. This is the last recurrence relation, right? F, right? So you can see that the first two recurrence relations are fundamental. Why they are called fundamental? Because they are obtained from that generating function independently, right? While these four, C, D, E and F, they can be obtained after some manipulation or modification in first and second, right? So this is it for this video. This is the orthogonality and recurrence relation of these Legendre's polynomials, right? In the next video, we'll be doing something more on series solution, maybe the Bessel's differential equation. That will be part of our next video. For this video, thanks.